So, hi everyone, thank you for coming out and giving us a little bit of your time. The way we're going to do this is I'm going to talk for a little bit, and then we're going to do a panel with some of our customers where we have some feeder questions, and then hopefully we'll get input from you guys. So we're really hoping for this to be an interactive session, and I'm going to start off by, I'm not going to focus on the software that I showed yesterday. I'm going to focus on kind of lessons that we've learned over the past 2 years making that software and how we think we're going to improve it and some of the lessons that we want to pull into the software. Okay? So I think, who here knows what reason codes are? Let's just start off with that. Okay? All right. So reason codes were the original sort of driver of all of this for H2O and for many other people that were making tools in this space. In credit lending and in several other types of regulated industries, every decision that the model makes has to be explained in terms of the original variables. Okay? So if I want to deny somebody a credit card, I have to say why, right? I have to say, well, your length of credit history is too short, your savings account balance is too low, and your credit score is too low. Okay? I have to give specific reasons for that person why we said no, right? And you can imagine that in a medical setting, right, if a machine learning algorithm is helping a doctor do something or saying something about a patient, people are going to want to know why, right? And so reason codes are these little values that we get for every prediction that basically says, hey, this is how much each predictor influenced this decision. And that's what we tried to do at first, right? Because that was the most burning need, right? How can a machine learning model be used in a regulated industry or an industry or organization where there was a need for high transparency? The most obvious, easy thing to do was to make these values that can then be used to generate reason codes. Okay? And we would call those local feature importance values, and they come from techniques like LIME or Shapley. So who here has heard of LIME? I asked this yesterday. Okay, so a lot of people have heard of LIME, and what about Shapley? Okay, so right, so those are the kind of techniques that we use on a row-by-row basis to try to say why the model made the decision it made. And with LIME, it's more of a guess, right? We're doing kind of more of a guess about why the model made the decision it made. And the great thing about Shapley, which came out, well, it's an old technique, but a very practical, faster implementation of it came out in late 2017, is Shapley's not a guess. Shapley is exactly why did the model make the decision it made for this person, right? So that's great. That's totally great. We're really, really happy about it. And what we've learned, though, is that interpretability is a much broader thing than just providing local feature importance values for each prediction that we make. Okay? So now what we know we have to do is take a much more holistic approach to making machine learning low risk from a financial and operational perspective and making it human-centered from, let's just go ahead and say an ethical perspective, right? Because as AI and machine learning become more and more common, right, in our lives, if AI, we don't know what it's doing, and we don't know if it's helping people, right? What is it doing? And that I assure you that is not a place that we want to go to as a society. Okay? So we really want to come up with a low-risk, regulation-compliant, fair, and fair is very, very hard to define. And I tend to use the phrase disparate impact. No, we don't want disparate impact. We don't want the model treating different people differently or more different than it should. So we want to come up with an interpretable, fair, and yet still accurate way to do machine learning, right? And that is the new goal. That's the new goal. So we gave people we hope that we gave people the values that they need to generate their reason codes, which is kind of a regulatory compliance issue. Now we want to do something more holistic, and we hope that that's going to be even more useful. So this is how we think we're going to do it. And some of the steps on this journey have already been completed. So maybe you saw some demonstrations of AutoViz, the auto visualization product. And that, that would be one way to accomplish this exploratory data analysis and visualization step, right? Now, what we need to do, if you've seen some demonstrations of driverless AI, it can make very complex features. It can extract very complex features from the data set. So we probably need to constrain that a little bit or come up with new, more interpretable kinds of feature engineering. Things like binning, things like sparse principal components. There are feature engineering techniques that are very straightforward and highly interpretable, and we probably need to introduce some of those into the system. And then we're very excited about this. The box below is constrained, fair, interpretable, or simple models. Okay? So there's a lot of commotion in machine learning right now around kind of Bayesian or constrained versions of classic ML models, right? So I might have a GBM, a gradient boosting machine, which is a very popular type of machine learning model, and I might constrain it to be monotonic with respect to each predictor. So I might say, as someone's savings account balance goes up, the probability that we want to lend to them also has to go up, right? So I can constrain the model's output to only go up or only go down as a variable increases. And we think that's that is an example of constraining a model to be more interpretable. There's lots of examples of this. So we get to work closely with our customers, and we're trying to develop, along with one of our customers, Wells Fargo, this XNN, okay, the explainable neural network, which is essentially a constrained neural network that's meant to be directly interpretable. Okay, so the mechanism of the model itself is directly interpretable. And I'm going to ask this question on the panel, and I'll kind of give a hint here. I believe less and less that there is a trade-off between accuracy and interpretability, okay? Especially on out-of-time data, right? I might be able to really fine-tune a very complex model on a static test data set, but when I apply that highly fine-tuned model onto out-of-time data, do we really think those gains in the second or third digit of AUC, are those really significant on out-of-time data, right? And my experience is no, but I want to turn this over to our panel, and I'd be interested to know if you have had a similar experience. You can see fairness or disparate impact analysis playing a role in this, and that's another very important topic in machine learning today. So, and again, this plays into lowering operational risk, okay? Who wants to be called out in the New York Times for having a discriminatory model, right? Who wants to be ridiculed on Twitter for having a discriminatory model, right? And if you are not doing this kind of testing, then you might have one of those, right? So not only is it just the right thing to do to not discriminate against people with your machine learning, but you need to do this to lower your operational risk, right? Your operational risk around model building. So we can kind of move through this diagram, but I think the best thing to do is for me to kind of pick out some of the highlights like I've been doing, and then we'll get the panel started so you can get some the people who are on the ground doing this instead of just thinking about tools for around this subject. But let me kind of give you just some of the highlights, some things that are a little bit different from what we might be doing today. So the first thing I called out were these constrained machine learning models, and I think that's going to be very important moving into the future. You only want as much complexity as you need, right? You don't want more complexity than you need. Complexity is risky because you don't know how the model is going to behave once it's out there in the wild if it's overly complex. Okay, so that's why I think these constrained or Bayesian variants of machine learning models are going to be very important. So moving through this, so we want to keep our feature engineering transparent. That's really, really crucial. You can do all the things on this little chart, but if your features are not comprehensible, then it's all useless. Okay, so we have to keep every step. We have to keep every step of the process interpretable. And I want to emphasize that I'm believing less and less that that means less accurate somehow. Okay, there may be a small accuracy penalty to pay, but I would say it's oftentimes insignificant, especially in these high or low signal-to-noise ratio problems about human behavior. Okay, we're not doing deep learning. My input data is not HD images. My input data is extremely noisy because people behave in strange emotional ways, right? Sometimes I buy the candy bar, sometimes I don't. I don't know why. So keep that in mind, right? We're dealing with these low signal-to-noise ratio problems, oftentimes about human behavior, or equipment breaking down under really strange scenarios, something like that. So I'm not talking about deep learning. I'm not talking about a high signal-to-noise ratio problem. So we want to keep our feature engineering straightforward. We're not doing deep learning. We're not trying to extract some kind of optimal, nonlinear representation of the data. We just want to use good features, but features that are also interpretable. This would be a new aspect of machine learning research where, and it's so new that I'm not even sure who would be interested in doing this. It may be really unpalatable to certain customers, but you can actually reweigh your data before building the model to reduce the disparate impact, right? If you are trying to make predictions that are not discriminatory against groups of people or other types of groups, then you can actually reweigh your data before you train your model to try to make that happen, right? And I don't know if that's palatable to people to change their data before training the model, but it might be, and that's something that we're going to consider. Then we've talked about the constrained models. And from the constrained models, we go to just kind of standard assessment, right? How accurate is my model? What's the ROC? What's the lift? What's the RMSE? And what are the residuals, right? This kind of just traditional, no-nonsense model assessment, I think it's super important. It's a solved problem. We just need to do it. And it's in driverless AI today. From there, we go to model debugging. So model debugging is a newer field where we want to treat our machine learning model like the computer program that it is. And we just want to see what kind of errors it makes and get rid of those errors. Okay? And there's lots of different techniques for doing this. One of the easiest ones that everyone should do, in my opinion, is you just test your model on data that it's never seen before and see how it behaves. Okay? That's one of the easiest ways to do model debugging. Right? The highest income my model saw in training was $400,000. What does it do when it sees an income of $1 million? It might not say what you think it's going to say because machine learning models do not extrapolate linearly from the training data. They can actually do all kinds of crazy things outside the domain of your training data, and you need to test explicitly what they're going to do in these situations. So that's just an example of a very easy kind of model debugging, and something that we have implemented through our code APIs, but not in the GUI yet. So post-hoc explanations, that's the thing that I was talking about yesterday morning, and that's the reason codes, right? And I will pause here really quickly to show you why we're so excited about Shapley values. Okay, so Shapley values are a way to decompose a model prediction into its individual constituents. And it comes from game theory. It comes from a coalitional game where people can cooperate. Can I break down the contribution of each individual to the outcome of the game? Yes, they figured out how to do that in 1953. Okay, it took us until 2017 to figure out how to do that in machine learning. So, just like to point that out. But you can see there is a history of literature here, which I think is really important for building the case in regulated industries that this type of local feature importance can be used, okay? So you can see the evolution of this over time. I didn't show, the probably hundreds of papers about Shapley values that happened between 1953 and 1988, but the 1988 reference there is a book, and for which, this massive body of work, Lloyd Shapley won the Nobel Prize in 2012 in economics. So this is a time-tested technique, and it's really just kind of our fault that machine learning is just now waking up to it. And these slides are going to be publicly available, so don't worry about that. All right, so now, the next thing is this post-hoc bias assessment or bias remediation. And again, I really even hate to use the words bias and fairness because they're so complex. We just really like to talk about disparate impact. Is the model behaving differently for different groups of people in a way that it shouldn't be doing? And those are fairly easy tests to do. And we have some open source examples that you can look at. We have some examples using the driverless AI, Python API. These are fairly simple tests. Now, you need to understand your data to understand the results of the test. But this is something that I think probably everybody who's doing machine learning should be doing, right? Sensitivity analysis, disparate impact analysis. You're going to get yourself into big trouble if you're not doing these things. And all the credit scoring banking people in the room are like, yeah, no doubt, we've been doing all this for 20, 30 years. And that is true. Like, I'm really just pitching to you this, this workflow with some minor, new research tweaks, this workflow that's been kind of perfected in credit scoring, okay? So next is human review. And the way that we handle this in driverless AI is by building a document that reflects all the stages in the modeling process that a human can read over. That typically someone who works in model validation would get this report and read over it and decide if the model was good from a kind of holistic perspective and good on some details. So I saw, I was just recently talking to a customer who works in banking and looks at models, tries to validate models, and he gave an example of, sometimes it's not about Shapley values and disparate impact analysis and sensitivity analysis. He said he had a model turned into him that was supposed to be about predicting losses on car loans, and the model didn't have the variable for the price of the car in it, okay? So it's just kind of, we did deep learning, but we forgot to put the price of the car in the model, right? And so if you have a document that collects all of the important information about the modeling process, then a human can review it, okay? And I think that's very important. We are not at the stage yet where we want computers thinking for themselves, and we may never want to get there. So after human review, we have to deploy the models, okay? And this is something when I teach my students, I like this thing that I like this kind of workflow process that I drew for them last week, and it was just completely accidental. It's like you do your ETL, you get your data together, you do your feature engineering, you train the model. All of that just costs your company money. All you're doing if you're a data scientist is spending your company's money when you do that stuff. So you have to deploy the model so it makes or saves money or derives value in some other way for your organization, or else you've just burned a lot of time and money, okay? So, and once the model's deployed and out there in the real world making decisions, you have to watch what it's doing, okay? Because if you trained your deep learning model and it's super tuned in to February's data, but you deployed it in April, it's not going to do very well. And as time goes on, it's going to do even worse. And so you have to monitor these things. And typically, if people are able to do model monitoring right now, they really only model for accuracy. They really only monitor for accuracy. So I would like for people to be able to monitor for fairness and even for interpretability as time goes on. And two more points here, and then we'll start the panel. Human appeal. This is super crucial, and people don't think about it. But there was an example recently where there's an app for babysitters. And if the app said you're a bad babysitter, and you're a nanny, there was nothing you could do. There was no way for you to appeal that. How unfair is that? How unethical is that? And so we have to come up with a way, whether it's an app on your phone or something like that, for if these models are making decisions about human lives, there has to be a mechanism for appeal, right? Or else you're just being unethical. So that's something that I'm not sure is productizable. I heard a good idea yesterday about just having an app on people's cell phones to have them kind of be able to file appeals or say, yes, I disagree, no, I don't disagree. But it's a crucial part of this workflow. And then the next part is iteration, right? We all know that these data science work processes are highly iterative. And the thing I'm sort of advocating there is we don't just think about improved accuracy, right? In each iteration of the model, you have to continue to think about disparate impact. You have to continue to think about interpretability. And so even if you lose a little bit of accuracy, but your next model is more interpretable, that might be, maybe that's a better gain than actually an accuracy gain. It could be in some cases. And I just want people to be able to think about extending their KPIs for machine learning away from accuracy on a static test data set to disparate impact analysis, to interpretability, and then also considering accuracy. So I think with that, I'll pause. We can do some questions, or we can just get the panel set up. Are we good? Or do you want to
address questions in the panel?
Whatever you want to do.
Well, considering it's your panel,
Okay. Yeah, sure. We can do the questions in the panel.
Okay. Wonderful then.
But if anybody just wants to raise their hand and ask a question, that's fine.
Okay. Well, let's do this then. We have a couple questions in Slido.
Okay. How can I see them? Okay, top question is there a mathematical definition of interpretability? That's a good question. I'm not aware of one, but it's not like people have never thought about this. So there's something called the VC dimension, which is an old machine learning theory type measurement, but it basically is a good measurement of how complex a model is. And we tend to think that the complexity of a model is inversely proportional to the interpretability of the model. So if a model has a ton of parameters or a ton of rules, that probably is telling you that it's less interpretable. So the more rules, the more parameters, the less interpretable in many cases. Another thing that we think about is the functional form of the model. We like to think of linear models as being interpretable. We like to think of monotonic models as being interpretable. So there are things that you can do to kind of talk about the interpretability of the model, but in terms of just one number to say whether it's interpretable or not that I'm aware of. Not that I'm aware of. Is MLI only available in driverless AI? Very good question. As an interactive dashboard, yes, it's only available in driverless AI. But we have tons of open source resources around this that we're happy to share, and I can flash it up on the screen when we move on from the questions or something like that. But just come by the booth or come talk to me afterwards, and I'll show you where you can get some open source resources for this. And there's tons of open source packages to do this, just tons. I'm not condoning that you use all of them, but if you Google it, you'll find something. Is this an industry standard for data science acceptable to regulators? Probably not. We don't know if it's acceptable to regulators because it's very new. It's very, very new. And so what I can say is the flow that I showed you is based on a workflow that is acceptable to regulators. But I think it's an open question for the industry as a whole. If I start using these complex machine learning classifiers, if I'm using Shapley values or other ways to get local feature importance, how are the regulators going to handle that? And my understanding is, it's about much more than math, right? It's about, can you show that you understand the process and that you can deal with problems if they come up, and that there's a lineage of the model, there's a lineage of the data. So when we're talking about whether this is going to be acceptable to regulators or not, it's a much bigger question than just, is the math okay, right? It's about the entire process and the documentation of the process and the iterations of the process. So it's a good question. Oh, and here I'll show, here's the resources. So this is all open source. The bottom two are all open source things that you can download and look at and play with.